Applying properties prove that the value of the determinant is equal to a plus b plus c whole square. The determinant is given as the elements of the first row are a minus b minus c 2a 2a. That of the second row are 2b b minus c minus a 2b, and the third row are 2c 2c and c minus a minus b. Now we want a plus b plus c. Look at it carefully. If you add r1 plus r2 plus r3 here, you have a minus b minus c. Minus b and 2b, so 1b will cancel and you will get plus b, and similarly plus c. So you may add r1, r2, r3, or maybe even no. c1 plus c2 plus c3 will not give, because you will have 2a plus 2a, 4a and 5a. You will not get a plus b plus c. Sorry. So the only possibility here, the very first step is important, that to row 1 you add r2 and r3 also. So replace r1 by r1 plus r2 plus r3. I am doing directly, I can show you here. The one element is a minus b minus c. You are adding 2b and 2c to it. So obviously 1b will cancel and you will get a plus b, 2c minus 2c, c. So you will get a plus b plus c, and similarly in the other terms of row 1. So you get in the first row, that way you will get a plus b plus c, a plus b plus c, a plus b plus. All the three elements will be a plus b plus c. And of course keeping row 2 and row 3 the same. C, c minus a minus. Now anybody can make out what should be the next step. Take a plus b plus c common from r1. Take a plus b plus c common from row 1. So you get a plus b plus c. The elements of the first row are 1, 1, 1. In the other two rows, that is 2b, b minus c minus a, and 2b. The elements of the third row are 2c, 2c, and c minus a minus b. Now what do you observe here? That all the three elements of row 1 are 1, 1, 1. In the previous question, when you had the elements of C1 as 1, 1, 1, we said R2 minus R1, R3 minus R1. And now if the elements of a row are 1, 1, 1, then we will take column 2 minus column 1 and column 3 minus column 1. That's how you will get 2 zeros. So apply C. In this case we will take C2 to be changed by C2 minus C1, and C3 will replace by C3 minus C1. And we get, of course, the value of determinant a plus b plus c. Already we have got there. And now applying C2 minus C1 and C3 minus C1. So at least C1 will remain intact, 1, 2b, 2b. And C2 minus C1 will make it 1 minus 1, 0. And b plus c minus a, just c aside. B minus c minus a, you are trying to make C2 minus C1. So b minus c minus a and minus 2b. So b minus 2b will make it minus b. So what do you get? Minus a minus b minus c. You can always try this step in rough. So if you take minus common here, you will get a plus b plus c. Please try this yourself. And of course 2c minus 2c you get 0. Similarly for c3 minus c1 you get 1 minus 1 as 0, 2b minus 2b 0. And what about c minus a minus b? Like in the previous case, c and minus 2c will make it minus c, and taking minus sign common, you will get minus times a plus b plus c. And now, because in row 1, you already have 2 zeros, so why not to expand along row 1? So expand along row 1. Expand along row 1. What do you get? 1 factor a plus b plus c is already there. Now when you expand, with row 1, you get one time, minus a plus b plus c and minus, so minus and minus plus, so you get a plus b plus c whole square and minus 0. And what about the other elements? Other two elements are already 0, 0. So you get a plus b plus c and a plus b plus c whole square you get from the bracket inside. So finally you have got your answer, that is a plus b plus c whole cube, which is the required right hand side. Now using properties, show that the determinant equal to 2 times x plus y plus z whole cube. It is almost same as question 11 first part. Now what is the determinant given to you? The elements of the first column are x plus y plus 2z, z. That of second column are x, y plus z plus 2x, x, and third column are y, y, and the last is z plus x plus 2y. Now look at it very carefully and let me know how can you get 2x, 2y, 2z. If you add r1, plus r2 plus r3, no, you will get x plus y plus 4z. What if you add c1 plus c2 plus c3? X and x 2x, y and y 2y, and 2z is already there. So yes, we have got the hint. We should apply c1 to c1 plus c2 plus c3. That is, to column 1 you add column 2 and 3. And in the column 1 you get 2x plus 2y plus 2z. Allow me to take 2 common directly. So you get 2 times x plus y plus z. And the yz here. And similarly, here you get 2x plus y plus z and y plus z plus 2x and y as such. And here also you have 2 times x plus y plus z, x and z plus x plus 2y. Okay, so now anybody can think, what is the next step? Take 2 times x plus y plus z common. Taking 2 times x plus y plus z common from column 1. So you get 2 times x plus y plus z common. You get column 1, 1, 1, 1. Column 2 you have the same, that is x and y plus z plus 2x, and in column 3 you have x. Column 2 the last element is x. Similarly in column 3 you have y, y and z plus x plus 2y remain the same. And now, we have got 1, 1, 1 in column 1, so what should you do? Subtract row wise, keeping row 1 intact. So you replace R2 by R2 minus R1 and R3 minus R1. That is, from row 2 and row 3 you subtract row 1. What do you get? 2 times x plus y plus z is already there. Now R1 we are keeping as such, 1xy we are keeping as such, and R2 minus R1, 1 minus 1 0, y plus z plus 2x minus x will make it y plus z plus 2x minus x will leave x, and y minus y no doubt is 0. Then R3 minus R1, 1 minus 1 0, x minus x 0 again, and z plus x plus 2y. 2y minus y will make it y. So z plus x plus y. And obviously, now you may expand it with first column or the third row. So better you expand with along first column. So now we can expand with along C1. So 2 times x plus y plus z is already there. And when you expand, you get 1 time. Both of them are actually x plus y plus z only. So y plus z plus x or x plus y plus z into x plus y plus z is x plus y plus z whole square minus 0. And the other two elements are clearly 0, 0. So finally you get 2 times x plus y plus z, and inside the bracket also gives you 2x plus y plus z whole square, and here you get the answer as 2 times x plus y plus z whole cube, and which is the required right hand side.